Hello everyone, I am Milan Sil from Indian Center for Space Physics, Kolkata, and I would like to share my presentation on fate of identifying noble gas-related species in the Crab Nebula environment. So Crab Nebula NGC 101952 is a freely expanding remnant of the historical supernova AD 1054, and it is containing both atomic and molecular hydrogen, electrons, and a region of air plus emission. And hydrogen is ubiquitous in the universe, and its very high abundance is explained by physics on grain surface. Several H2 emitting knots have been identified in this crab environment, and where kinetic gas temperature is of the order of 2000 to 3000 Kelvin. And Richardson et al. 2013 first modeled some H2 emitting knots in this environment. And they suggested the formation of H2 molecule that hydrogen atom reacts with abundant electron to form hydrogen anion, and which is again react with hydrogen atom to form H2 molecule. And after that, Barlow et al. 2013 first identified the first interstellar noble gas molecule, argonium ion, in the Crab Nebula environment with its J equal to 10 and J equal to 21 rotational transitions, and using Herschel Spire instrument. And they also identified a prominent transitions of OH plus strong emission in the same environment. And after that, Silke et al. 2014 identified the rotational ground state transition J equal to 10 in absorption towards several continuum sources like Sagittarius B2M, Sagittarius B2N, W31, W51, W49, etc. And Shilke et al. 2014, they also they cannot observe the any H plus rotational transitions in this environment, in the same environment. And After that, very recently, the discovery of first molecular ion in the universe, which is HeH plus, identified by Guston et al. 2019. And they identified this HeH plus rotational ground state transition J equal to 10 using great instrument on Sophia towards the dense young planetary nebula NGC 7027. And why it is the first molecule in the universe? Because after Big Bang, when the temperature falls below the 4000 Kelvin, due to high ionization potential of helium, it neutralizes faster than hydrogen, and this neutral helium react with a proton to form HeH plus, which is the first molecule formed in the universe. And about approximately 100 years ago, the HeH plus HeH plus was found in the laboratory, and by Black 1977, it was speculated that it could be in the interstellar medium also. And these two observations actually these two observations inspired us to model this noble gas molecular ion on not only the hydride cation but also the hydroxyl cation towards this Crab Nebula environment. And for this, first we want to check the diffuse interstellar medium modeling, because in the diffuse interstellar medium, Shilke observed the ARH plus molecule. And for this, we model using the cloudy spectral synthesis code with its version 17.02, latest version by Farland et al. 2017. And for this modeling, we used initial total hydrogen density of the order of 50 per cubic centimeter, cosmic ray ionization rate of H22 into 10 to the power minus 16, interstellar radiation field of 1 Rayne unit, and this initial elemental abundance. And this is the spectral energy distribution we used in our model. And in this spectral energy distribution, you can see the 1 Rayne unit is interstellar Rayne radiation field, and this is the small window is the extinguished by cold medium. And from our modeling, we can check that the extension to gas ratio is of the order of 5.412 into 10 to the power minus 22 magnitude centimeter square. And this is the diffuse interstellar medium modeling results. Here you can see that the cloud is going to molecular with increasing depth, and where the temperature varies from 50 to 20 Kelvin. And this is and you can see also from here that the carbon atom C plus carbon ion converts to carbon atom in the in depth into the cloud. And air H plus is a unique tracer of H2 by anti-correlation and also by atomic cloud with its correlation. You can see from here that H2 is increasing with the visual extension, but AR H plus is decreasing with visual extension, so it anticorrelates with H2. And any H plus, which is the red dotted line, any H plus is also decreasing and following the AR H plus abundance trend. And here we also present the abundance of OH plus, HEH plus, and several hydroxyl cations. And for this modeling, we used a broad chemical network in our model. We modified some network, added the neon chemistry network, and also developed and modified some argon and helium network from Priestley et al. 2017 and Neufeld et al. 2020 and Gusten et al. 2019. And from our diffuse interstellar medium modeling, we check the column density of several simple molecule and ions, and check that the column density matches with observation, the observation results for W51 cloud by Indriolo et al. 2012. And also from the modeling results, you can see the air plus and air H plus, air plus and air H plus profile matches with a Silke et al. 2014 observation. So our model is reproduced by Schilke observation, and after that we use our modeling for the Crab nebula environment. And for the Crab nebula environment, we used these physical conditions where we used inner radius is 2.5 parsec, and from the source, and cloud thickness is roughly of the order of 3.5 into 10 to the power 16 centimeter. So you can see from here that inner radius is very greater than the thickness of the cloud. So it is a plane parallel geometry we assumed here in our modeling, and these are the elemental initial abundance used in the cloudy modeling for the Crab. And this is the spectral energy distribution. Here it is for the interstellar radiation field in 31 Rayne unit, and this is the X-ray intensity used in our spectral energy distribution. And luminosity is used roughly of the order of 10 to the power 38 arc per second. And type of grains, we used amorphous carbon grain, which is modified according to Wen and Barlow 2015 paper. And dust to gas mass ratio is kept 0.027. And for the Crab nebula environment, we also modeled radiative transfer model. And for the radiative transfer model, here we plot actually the air H plus 21 and 10 transition ratio. Barlow et al. 2013 observed this ratio is of the order of 2, And here by radiative transfer modeling, we want to check the parameter space in which electron density and hydrogen density and which temperature this ratio is reproduced. For this modeling, we used the column density 1.7 10 to the power 12 per centimeter square from Hamilton et al. 2016, and FWHM line width 5 kilometer per second. And you can see the left four panels where H2 density is kept constant at 1 cubic centimeter, and four window is for four temperature, electron temperature 10 Kelvin, 100 Kelvin, 1000 Kelvin, and 3000 Kelvin. And for 10 Kelvin temperature, you can see that there is no population of the transitions ARH plus 21 and 10, because the upstate energy of 10 transitions is roughly of the order of 28 Kelvin, and 21 transitions roughly of the order of 88 Kelvin. So with increasing temperature, the energy level populates, and in when temperature is greater than 100 Kelvin, the electron density is of the order of 10 to the power 3, and hydrogen atom density is roughly of the order of 10 to the power 6. And in 100 Kelvin temperature, hydrogen density of the order of 10 to the power 7, and electron density of the order of 10 to the power 3. So with increasing temperature, you can see that the hydrogen density decreases and electron density is increasing. And the right four window is for fixed temperature 2700 Kelvin, and when the hydrogen density varies for 10 to the power minus 2 to 10 to the power 4. And you can see that with varying hydrogen density, hydrogen molecule density, there is no effect on the molecular line ratio. So from here we can conclude that the main collisional partner is electron in this environment. And though we considered here electron, hydrogen atom, and hydrogen molecule, the hydrogen molecule collision partner is not dominating. And also in the public version of Radix, we cannot consider here the reactive collision of H2. So from our cloudy modeling, we calculate the intrinsic line surface brightness of the crab. And for this, we plotted again the parameter space, where y-axis is the cosmic ray ionization rate, and x-axis is the total hydrogen density. And you can see that the observed surface brightness is indicated in the upper panel. And you can see from here that at density roughly of the order of 10 to the power 4 to 6, and cosmic ray ionization rate of the order of 10 to the power 6 to 8, we can match the observed line surface brightness of the crab. So and after that, from parameter space, we find the best fitted zone, and for the best fitted zone, we plot this abundance of simple molecules. You can see that the temperature of the crab is varying roughly of the order of 4000 Kelvin. Sorry. And these are the other simple molecules abundance, and these are the noble gas molecule ion, and both hydrate and hydroxyl cation. And in our network, it is important to mention that we cannot consider here the we cannot consider here the isotopic fractionation reaction. And so the initial elemental abundance of isotopes are reflected in the final abundance. And these are the emissivity of the crab we calculated. And from here you can see that the strongest OH plus transition, which is 308 micrometer, is and the 36 ARH plus transition 242 micrometer, that is 2 1 transitions, is above the 308 OH plus transitions, and 485 micrometer transition is below the 308 micrometer transition, which agrees well with the Barlow's 2013 observation. And we also calculate the emissivity of several transitions of hydroxyl cations of noble gases. And after that, from our surface brightness calculations, we plot and compare this with the OH plus surface brightness, and checked the detectability of the hydride, these three hydride cations in the Crab nebula environment. And for this, we actually calculate the atmospheric transmission, and also the optical depth and surface brightness. And from our calculation we plotted here, and from here we conclude that several transitions of hydride and 36 ARH plus, 20 NEH plus, and HEH plus could be observed using space-based SOFIA observation. And these atmospheric transmission is calculated in the SOFIA height, which is 41,000 feet. And we also calculate some spectroscopic parameters of these hydroxyl cations of several uh, isotopes with their several isotopologies, and this could be helpful for future detection. So in summary, in the diffuse ISM, we found that ARH plus, NEH plus, and HEH plus fractional abundance is reasonably high and could have been identified. The abundance of 36 ARH plus, 20 NEH plus, and HEH plus are comparable to the abundance of OH plus in the Crab filament. And considering the upper limit of the formation rate, which is of the order of 10 to the power minus 10 per second, we obtained reasonably high abundance of the hydroxyl cations of noble gases. However, using realistic rates, which is calculated using Bates equation of these reactions, we obtain very low abundances of these hydroxyl ions. It is thus important to accurately measure and estimate these rates, and a high value of cosmic ray ionization rates of the order of 10 to the power 6 to 7 per second, and with a total ratio is roughly of the order of 10 to the power 6 to 7, and a total hydrogen density a few times 10 to the power 4 to 6 per cubic centimeter can successfully reproduce the absolute surface brightness of the two transitions of 36 ARH plus by Barlow et al. 2013, and the strongest transitions of OH plus, which is 308 micrometer, and the H2 emission 2.12 micrometer reproduced well, and also several atomic and molecular transition ratios could be reproduced. And optical depth of most of the probable transitions of hydride and hydroxyl cations of noble gases fall in the observed range of Herschel Spire and PAC, Sophia, ALMA, VLA, IRAM 30 meter, NOEMA, which were calculated for the Crab, and noticed several transitions of hydride cations of noble gases are most likely to be identified with a space-based observation like Sophia. However, the fate of detecting hydroxyl cations in a similar environment with a similar facility is very difficult. And calculated ground state vibrational and equilibrium values of rotational constants and asymmetrically reduced quadratic centrifugal distortion constants for various isotopologies of hydroxyl cations of noble gases are calculated, and provided this constant for HEOH plus hydroxyl helium hydroxyl cation for the first time, which was not available until now, and provided some catalog files as per JPL style for various isotopologies of hydroxyl cations, which might enable their future astronomical detection in other sources. So I would like to acknowledge my collaborators for this work, and I also want to thank COSPAR and DST Inspire for providing financial support, and thank you for your kind attention. I will be happy to take questions. Thank you.